Today we're going to learn how to do magic. No, not exactly. We are actually looking at uh, gravitational field and electric field. They are just like magic because you can see things like an apple falling down from a tree to the earth. So there's no string that is tying to the apple, but you just get attracted to the earth. Another example is the moon. It just keep moving around our sun, our earth. So there's no cable, uh, there's no string. Okay, there's just an invisible thing that's in between that keeps the moon orbiting around the earth, and the earth orbiting around the sun, and the sun or the whole solar system is orbiting around a black hole, and so do other planetary systems that move in such a way. So the same things go to charges. So I think you might have played this before in your secondary, where you rub a comb and then you place it under a flowing water, beside a flowing water, and you can see uh, the stream of water will get attracted to the comb, the charged comb. You can try it out using the tap in your house, since now we can access to the lab. And you charge the comb also, and you have some small pieces of paper that it will get attracted to the comb. So other case where you've seen before, maybe the screen of your TV, that when you get near to it, your hair might get some of the strand of hair might get attracted to that. Boys cannot, maybe too short. All right, so this is like magic. There's nothing in between. It just happens like this. Okay, of course, in terms of physics, is because of exchange of particles. We're not going into that. That is a bit more in depth. Okay, so today we'll focus on electric field. Just like the football field, where a ball experiences a force when you kick it around. Okay, inside electric field, that's where charge, not the ball, the charge experience force. Okay, just an analogy. So it's a region of space. This is definition. Yeah, it's a region of space where a charge experience a force. So as animation down here shows you that we have a positive charge, and in the space around it, suddenly we place a negative small test charge into that, and then you get attracted to the positive charge. Okay, so this charge experience a force by the positive charge. And because it's invisible, people need something to see. So that's why scientists invented this thing called the electric field. Even electric field and gravitational field, these kind of terms is termed by human, and then lines is invented so that people can see and understand the meaning behind these lines. Okay, so there are some rules because you need to draw that. So here are some rules that you need to follow, and I will further elaborate that when we come to the example later. So it starts at positive charge or infinity. Second point is that it ends at negative charge or infinity. The third point is that the density of the lines, as in how close they are they very far away or are they very close together? So it gives you a meaning of how strong is the field. If you have more lines in a certain region, that means it is the field strength there is stronger. And these electric field lines, they never cross. Okay, when we draw electric field lines, or when we simulate electric field lines using a computer, it will never cross. Okay, so first of all, let's look at electric field lines of a single charge. So I have a point charge here. We can ignore its dimension. It's just a point charge plus q. So as you draw, you need to draw a radial line. Radial line means that the line is continuous, extending from the center of the point. Okay, so here's an example here. So you can see that the arrow is pointing out. So it starts at a positive charge, and where does it go? It go to infinity. So it's end at infinity. Okay, start at the charge and end at infinity. All right, and if you look at the second one here, this is the -2 charge. That means it's 2 times greater than the case of A. So you can see more field lines, and more field lines means it's more dense, indicating that this one at any region around it must be stronger than the case of A, and that makes sense because it has 2 times the charge, right? So this one, it ends at negative charge. So that's the second line in the rule just now. It ends at the negative charge, and it starts from infinity. Okay, it starts from infinity. That's probably positive. Okay, somewhere very far away. All right, so here's the description that I mentioned just now. So here's the thing: why is it that we need to say that arrow is pointing out from a positive charge? Why not pointing in? And negative charge we draw pointing in. Why not pointing out? Okay, so you might have you might have thought of this. How come we cannot draw the other way? The first thing is that if you draw the other way, then it'll be very confusing, because your friend might be drawing positive as going out, the line is going out from the isolated charge or point charge, but you are drawing a positive charge that is pointing in with the lines pointing in. So that's very confusing. So what is confusing is that's why we have to define something in behind this meaning of the arrow. Okay, so meaning of the arrow is that you need to remember this because it's quite important. It's actually showing you the direction of force when we place a positive charge inside. So let's say I place a positive charge here. So the arrow will tell me that, okay, this charge will experience a force in this direction. Okay, if I place a positive charge here, okay, this one will also experience a charge, experience a force in this way. If I place a positive charge here, then I know that according to this arrow here, it is experiencing a force that is towards the negative charge. All right, so then you might be thinking, what about if I place a negative charge there? So if I place a negative charge there, so very simple, because the arrow represent for positive, the opposite of this arrow will represent the force on the negative. And same thing to here, the arrow represent the force on positive, therefore if you have a negative charge in that region, it will be opposite to the one indicated by the line. Okay, so therefore we only need one direction, and we fix for everybody just follow the same thing. And if you have a negative charge, then it will be just in the opposite direction of the arrow indicated. All right, let's move on. And if we have two charges in that region, so we have these two charges in this region here. Okay, so start at positive and end at negative. If I put a positive charge here, somewhere here, so its direction of force will be the tangent of this line, and it follow the direction. So if I have a positive charge here, it will be tangent of this line somewhere here. If I have a positive charge here, it will be this one. So it just follow the direction of the tangent line. Okay, so all positive charge. Alright, so you can imagine that it get repelled from a positive charge and going towards the negative charge. Alright, so it might be very difficult to say to decide how I draw so that the line doesn't cross. Okay, everything actually start at the center here, the starting here. That when you draw, you have to make sure that it start with a direction perpendicular to the surface. Sorry, I can't zoom any more larger, so I just draw somewhere here lah. So let's say this is the surface of the positive charge. As you draw, right, you need to make sure that this is 90 degrees. This is 90 degrees. Okay, you need to know how to draw this. It might come out in an exam question. Alright, so make sure you follow this rule, that it is perpendicular to the surface at that point that you are drawing. Okay, so let's move on. How if we have two positive charge? So they will repel each other, and the line cannot cross, so therefore it will be all pointing out, and they are like avoiding each other in the region facing them. inside here, so they are trying to avoid each other. Okay, so they never cross also. That's the case for two positive charge, and also two similar negative charge also can. Right? What if you put a positive and negative charge in a region like this? So again, the same thing. We just need to make sure that the arrow is pointing to the correct direction, and the density of the lines is reasonable. So as in those that are near the positive 2 charge, they are more dense. Those that are near the negative charge, they are less dense. Okay. Okay, so the other cases is like if you have a charge plate and a single charge or point charge. So it will look something like that. So pointing out from the positive plate and going towards the negative charge. Or we have a case like this, negative plate, positive charge. So we'll be pointing towards the negative plate and out of the positive charge. Alright? Okay, now let's try to play a quick game. Okay, I'm going to show you a few diagrams here. Inside there are some charges and there are few lines. So you need to identify which charge in each case has a greater magnitude of its charge. Okay, so I'm going to show you two charges, left and right, and there are few lines. So you need to identify which one is greater magnitude in terms of its charge. Okay. All right, you have about 1 second for each case. Yeah, let's start. Okay. Alright, so you got the answer. So first one, of course, is the one on the right hand side here, because there's more lines. Second one is the one on the right hand side also, because it has more lines. The third one, also the one on the right hand side. And the last one is the one on the left hand side. Okay, so I'll see you in the next video.